In this video, we're going to talk about hypothesis testing for the population standard deviation. So it's very similar to the ones we did where you're testing for the population proportion of people of whatever category you're talking about, or the population mean that we used. There is going to be a little bit of a hiccup though, because as we saw in the confidence interval, when you're talking about standard deviation, you have to use the chi-square distribution, and there is not a good hypothesis test in your calculator for this problem. And you might say, wait, I looked in the menu, I saw a chi-square test, but the thing is that chi-square test is actually for something else we're going to see, not for this section. So we're going to have to do the p-value kind of a little bit more ourselves. What it means, we have to calculate the chi-squared value for our sample ourselves here. So this is the formula that we use for calculating the chi-square that we're going to need in this section. So I'll put that on the side there so we can use it later. And let's first talk about how do we set the null and alternative hypotheses. Well, just like before, your H0 is always going to be, in this case, the parameter sigma equals some number. And again, that number is going to be the prearranged value, the assumed value, whatever you think it might have been at some point in time. That's your default assumption for your sigma. And then you can have your left-tailed, right-tailed, and two-tailed, where you're trying to prove that sigma is less than the number, or you're trying to prove that sigma is greater than the number, or you're trying to prove that your sigma is not equal to the number. So let's look at this example below so we can set up the exact hypotheses for that. It says, investing in the stock market is always risky, but you would still like to make your risk as small as you can. And we're going to be measuring risk here as the standard deviation of the return that you get on your investments. So it says, suppose the standard deviation of the return for most investment opportunities is 5%. You believe you can pick these opportunities better than this and take a random selection of n equal to 50 of your investment choices and find a sample standard deviation of the returns to be s equals 4.6%. Test whether this data supports the hypothesis that the investment opportunities you pick have a lower standard deviation from most investments at the alpha equals 0.05 level of significance. So they give us some different numbers here. However, if you read it carefully and you're trying to figure out what is the standard, what is the default, what is the quote-unquote normal circumstance for what sigma should be, and they're saying that most investments are at the 5% range. Now you can actually write it out as 0.05, or you can just put it as 5 and understand that you're talking about percents. It just means that whether you're going to use s equals 4.6 or s equals 0.046. If you look up here in the formula, you're going to be dividing those two numbers. So as long as you use them in the same, like if both are in the decimal 0.05 and 0.046, or if both are in percents, 5 and 4.6, it'll still work out anyways. And then what is my alternative hypothesis here? We're trying to show that our picks are better. So we're trying to show that our sigma is less than 5. Okay, so now that we have this here and we've identified that it is a left-tailed test, in order to calculate the p-value, the first thing we have to do is we're going to have to calculate this chi-square number here. So n minus 1 is going to be 50 minus 1 times the s, which is 4.6 squared, over the sigma 0, which is 5 squared. So we go ahead and put this into our calculator here. 49 times 4.6 squared divided by 5 squared. And I'm getting a chi-squared of 41.47. Okay, 41.47. And we're also going to need the degrees of freedom here, which is n minus 1. So that's going to be 49. However, we need one more thing before we can put it into our calculator to get the p-value, and that's going to be realizing that, again, we have a left-tailed test here. And so what that means is if this is our 41.47, we want to talk about the left tail of it. So since we're going to have to find our p-value with our calculator separately, not just having it do all the work for us, we are going to do a chi-squared CDF function. Just like how once upon a time we did the normal CDF function. And they're going to ask you for the lower and the upper. And this is where you really need to know that it's a left-tailed test, because the upper region, that's where the 41.47 is. And the lower region, you're going all the way down, so that's why it's going to be essentially a negative infinity there. So let's go ahead and actually show you how to do that in the calculator now. So we got 41.47 and 49 degrees of freedom. So to get into the chi-squared CDF, we're going to hit second vars. And then we're going to scroll down, and you're going to see not chi-squared PDF, you want chi-squared CDF. And now the lower, now you could think of putting in negative infinity, but if you remember about chi-squared, it starts at 0. So negative infinity is what you put in when you go all the way to the left on a normal variable, but for the case of chi-squared, you can just put 0 there. And then your upper was 41.47, and my degrees of freedom were 49, and we go ahead and hit that answer there, and we get 0.23. That means my p-value is 23%. So that means that even if our stock picks were the same for the true standard deviation of 5%, there still would have been a 23% chance that the ones we picked as a random sample would have been S's 4.6. So that means 1 out of every 4 times we tried this, it would end up giving such a good result. So that means that there is not enough data to really support our claim. It could have just been random chance. Now, again, that doesn't mean that we have proven that H0 is true. You are never going to prove H0 is true. We don't know that. All we can say is there is not enough evidence to support the claim that our investment choices are better. So this sample was not good enough to say that we are experts at investing our money. Maybe we really are. Maybe this sample is better, but we just didn't have the data here. It wasn't enough information to do that. So as far as we know now, we really aren't any better at picking stocks than the general market is.